Okay, so in this video, we're going to be looking at, we'll start with two-sided alternatives, and then we're going to get into quantitative variables and hypothesis testing. So in the previous videos, we looked at one-sided alternatives, which means we were interested in either something has increased or something has decreased. With two-sided alternatives, we're looking at either way, so increase and decrease any change at all. So for the new processing engineer, referring back to the first example, at the beginning of this chapter, may be interested in whether there's been a change in the cracking rate, not just a decrease. So we have the null hypothesis will still be the same. So that would just be P equals 0.20. And then the alternative now, instead of P less than 0.20 or P greater than 0.20, the parameter, of course, is always the same. And then this number is not going to change. This will also be the same. And now we're going to see if it is not equal to 0.20. And kind of implicitly, we kind of inferred this, I guess, when we started this with the one-sided, but it doesn't mean, so obviously 0.19 is not equal to 0.20. So what we mean by this and what we mean by less than or greater than in this context, we don't mean strictly any number that is not equal to 0.20. What we mean is the number far enough in either direction from 20%. So is 17% far enough? Is 24% far enough away? So it's not strictly, 0.1999. That's going to be not equal to 0.20. So, we must accept the alternative kind of thing. Is it far enough is kind of what we're looking at. Is it far enough away in either direction? From 20% in this case. So now if we draw this normal curve, we'll start at the 0.20 in the middle. The sample proportion, if you remember from the first page, is 17%. Now we're also going to go the same distance in the other direction. So same distance in the other direction, that'd be 0.23. And it's not really that important what this side would be. And a lot of times it's more trouble than it's worth to figure out what that number would be. It's not super difficult, but it's not really that important because the area, and like we said, we always shade away from the center on these hypothesis tests. The area over here is the same as the area over here. So if we call this A1 for area 1, we call this A2 for area 2. Area 1 is going to equal area 2. So it doesn't really matter what this number is. We know that this area, wherever this number would be, is equal to this area over here. So a two-sided alternative is just an alternative hypothesis in which we are interested in deviation on either side of the null hypothesis. And so if we look at an example, a student organization, oops. Where did I go? Too far. All right. A student organization that promotes diversity believes that the percentage of minority students is no longer 35%. In a random sample of 250 students, 97 of the students are minorities. Does this evidence support the organization's claim that the percentage of minority students is not 35%? So this kind of language is not that indicates that we're looking at a two-sided hypothesis. So we don't have a greater than language, we don't have less than language, we just have changed language. Another, it could say kind of like it said at the top of this page, has this changed? Is this unusual? Things like that. So pay attention to the words and how these statements are phrased, and what are the key words that indicate we're looking at a two-sided hypothesis. So following the same steps, and we'll probably skip checking the conditions, but step one, state hypotheses. So the null hypothesis is that P is 0.35. The alternative is going to be that P is not 35. So there are our hypotheses. Step two, and we'll go through these quickly. So we do have random samples. So the random is met, independence is met, and 250 students. So a student organization that promotes diversity. So this is actually looking at the entire school, I would assume. So the sample size is 250. Is 250 less than 10% of the entire school? And probably yes. So 250 would be 10% of 2,500. So is the student population more than 2,500 students? We'll assume that it is. So that one is met. And then n times p. So that would be 250 times 0.35. That is going to clearly be more than 10. It comes to 87.5. That is more than 10. N times Q, that would be 250 times 0.65. That is also going to be more than 10. So all the conditions are met. So we'll move on to the next step. Step 3, and all these steps, by the way, are going to be the same as the one alternative, except when we calculate the p-value, we're going to double it. And other than that, all the steps are the same. So step 3, if you remember, was find n, which we know is 250, then find p, which we know is 0.35, and then find p hat, which we know, or we can see the sample size is 250. Now of that 250, how many were minorities? So that's the 97. So p hat is 97 over 250. And as a decimal, that is exactly 0.388. So we're not rounding off here. And then standard deviation of p hat is the square root of pq over n, and q, if you remember, is 1 minus p. So this is 0.35 times 0.65 divided by 250. And that is 0.030166, and that one is rounded off. If you remember, it's always a good idea to keep 5 or 6 digits after the decimal so you don't have rounding errors when you use this number again later. So if you're going to use a number later, try not to round off at all. If you do have to round, then keep 5 or 6 digits, and that should save you from rounding errors later. Step 4 was to draw the normal curve. And so if you're good at doing the one-sided, this is really the only place that you have the potential to make a mistake. So we have the p in the middle, and then we're going to put the 0.388 over here. We always shade away from the center. Now, this is the part where people sometimes will mess up. This is a two-sided alternative, so we have to go over here. Now, again, we can figure out the distance there, go the same distance this way, but it's not important. So I'm not even going to try to figure that out or worry about it. But we know that this area over here is equal to this area over here. So we can calculate this area, which we're going to do in step 5 here. And then all we need to do is double it. And you can do that all at once. So on the graphing calculator, the p-value, and you can do this all at once or you can do it in 2 steps. It doesn't matter. But you can do 2 times and then go into the normal CDF menu on the calculator. So we're going to find this area, and then the 2 times is going to get this area and then multiply them together. So, so the lower bound is 0.388. Upper bound would be 1 for 100%, or you can go higher if you like. Mean is 0.35, and then standard deviation is 0.030166, and plug that in the calculator, and we get 0.208. And so we see that if you go to step 6, which is the conclusion, the p-value is not small. So if you remember, the standard value for p-value is 5%. We're going to get more into the 5% later in the next chapter, actually. But for now, just assume 5% is the cutoff. So this is above 5%, so that is not small. If it is not small, we reject the null hypothesis. And since we're going to reject, we're going to fail to reject. Let's fix that. Fail to reject. So not small, we do not reject. Null hypothesis, there is not enough evidence. Now just kind of restate what we're asking. So there is not enough evidence. The percentage or proportion of minority students has changed. And again, if the p-value comes out to be less than 5%, then you say it is small. You reject the null hypothesis, and then you say there is enough evidence to say the percentage has changed. So really, all you're doing, based on this, is either you're almost saying the same sentences, but either you put the not in or you don't. But you're saying the same things every single time. Do you negate it or not? That is based on the p-value here. All right, so we'll stop this one and then we'll do the quantitative variables in the next video.